Yeah, so today's talk is by Mike Sparrey and Julian Edwards from ABB, and we have Aidan joining us as well, who will be helping us at the Q&A section of the talk at the end. So the plan for today is that the talk will go for about 40-45 minutes, and then we'll have a section for Q&A towards the end of the talk, and we'll aim to be wrapped up then by 2 o'clock. If you do have any questions, if you can enter them in the Q&A box at the bottom of your screen. And yeah, just thanks for joining us, and also thanks to ABB, Mike, Julian and Aidan for joining us today. And I'm going to now hand over to Mike, who's going to speak in the first instance, followed by Julian later on. So thanks very much.
Thank you very much, Edith. Good afternoon, everybody. Good to be back to you again. Just to remind you, obviously, Mike Sparrey. I've been ABB 32 years, and my background is a chemist, and I look after the water industry in the UK, and I'm a director of SWIG. Obviously, my colleague Julian Edwards is with me today. He's my product manager. He's been with ABB with the water industry for 35 years, 15 years with ABB, and 20 years with Seven Services. So we kind of sort of split this this topic up today. I'll look at sort of ammonia and sort of give you our experiences of ammonia within the UK market and what's happening there. And then Julian will look at sort of mixed liquor suspended solids and total suspended solids, and where we are and what activities we've been doing within the UK. And we've got a few case studies as well, which hopefully you'll find interesting. So let's start off with ammonia. It's an interesting application because it goes really across both potable and wastewater within sort of the UK markets. You can sort of see on the sort of clean water side there would be sort of water intake, river intake. We'd have sort of chlorination, sort of treated water, and sometimes you can have final water if so needed. But certainly for us, it's the wastewater side that's been quite challenging, quite interesting, and quite different for us, which we've been doing a lot of work in the last sort of 3 to 4 years. And that sort of from industrial use, it could be final effluent discharge. We do a lot. We've done a lot of work within the sort of tertiary treatment work as well. And we haven't got anything today, but we're even looking at the sort of activated sludge air, which is a challenging application. So, like everything, why the need for ammonia measurement? Well, probably like yourselves, over here in the UK, we have a lot of farming, intensive agricultural, a lot of sort of ammonia products that are produced in fertilizers and chemicals. Obviously, a lot of ammonia is produced as sort of natural waste. But you can see that it's a pungent smell. It's extremely soluble in water. It's toxic to plants and it's toxic to animal life. So water companies with the Environmental Agency and the Drinking Water Inspectorate, there is a compliance consensus on the actual levels of ammonia that they're looking at. And you can sort of see on the right-hand side, if you're doing aerobic or anaerobic, if you've got anaerobic conditions, you will form ammonia. So you've got to make sure your process conditions are right. So it's a key parameter within the water industry to actually maintain, reduce. And one thing we are seeing in the UK is the consent limits are coming down. Okay, so therefore there is a regulatory review of this with the Environmental Agency, looking at any breach of consents. They will be fining the water companies. So there's many reasons why water companies are keen on this measurement. Looking at this slide, this is quite interesting because we as a manufacturer, we engage with our water companies, and many do frameworks, many do preferred supplies. But what you'll see here is on the left-hand side, sorry for the small print, but this is a specification from one of our water companies, and they're looking for colorimetric 0 to 3 milligrams ammonia. So it's very specific of what they're wanting. But on the right-hand side, another water company, because of the range 0 to 20 milligrams, a higher range, then we have to go an iron selective route. So from our side of it, from a manufacturing point of view, this guides us to kind of instrumentation that we can actually supply. So just a brief overview. So ABB have been operating these two ammonia monitors within industry for a good sort of decade, really. And on the left-hand side is our iron selective electrode. And you can see typically the dynamic range 0 to 1,000 ppm of ammonia. Key for industrial markets where they're typically 3 to 4, 500. Key for the wastewater side. But then we have the colorimetric analyzer, sort of 0 to 5, sort of the low level side. So you can see where if the consensus levels are coming down, we have to change the technology that we use. If we look at the iron selective, most monitors that we now produce these days, we have to take considerations what the customer wants. What are they looking for? They're looking for lower maintenance. They're looking for auto calibration. They're looking for reagents to last longer, and they're looking for servicing intervals to be as long as possible. It's about cost of ownership. And this is something that we've been keenly developing these products for many years to make sure that we do that. I mean, one of the key things on this instrument is that you can actually go 3 months without actually replacing reagents with an eco mode. So there's subtle little things that we do. You can see from here that common spares is a key thing for us, input diagnostics. So we're trying to help people actually look at these monitors and look after them. We're introducing this year QR codes, which allows people to remotely diagnostically look at the instrumentation, so therefore saving people from going out. So there's a lot of things that we're trying to do with these monitors. On the colorimetric side, we have the ammonia, obviously a colorimetric analyzer side. This could be programmed so your reagents could last up to 240 days on one measurement per day. So it all depends on what you need and how many times you're measuring the sample. Once again, like the ISC, we have scheduled maintenance. So we're trying to make things last longer and be more robust and reliable. However, that's the instruments, but let's sort of look at sort of the installation and sort of the sampling requirements, because depending whether you're in the clean water side or in the wastewater side, there are different challenges. So just looking at this slide here, we're looking at sort of the typical applications that we've seen, Julian and myself here, where there may be a pressurized main on the right, left side, top left, a V-notch weir, seems quite neutral sedimentation, an open channel that we've seen on river intake or finer effluent sort of type takes. And then we have the classic sort of turbulent chamber or deep chambers and sequential batch reactors. So there's different applications, different water courses that cause us many challenges. And you can see here some of the other ones here on a new one for us, or some work that we're doing is obviously the return to activated sludge that we've been doing some work, and then stormwater chamber overflows, which is a new one. And you can sort of see the little video here showing that, the kind of sort of sampling areas quite small. How do we get a sample out of there? How do we get it to our monitor? One of the key things here, and this is our experience with these types of applications, is in many ways, we have to be selective on what kind of filtration or sampling conditioning systems that we have. And you can see here, we can go from a manual cartridge system, submersible pumps or surface remount pumps, even just header pops or things. There's lots of little things that we do. And certainly for me, some of the case studies, I'll be utilizing some of these filtration techniques and just explain some of the challenges that we had and how we overcome them, whether that's direct or whether that's with a contractor or the end user. But you can see we can go from a sort of 400 micron filter right down to a 0.02 ultra filter. So all different applications can depend on what you need. If you look at this in the corner on the right-hand side, hopefully you can see this, but this just shows you an example of a debubbler. So we can be quite sophisticated. So let me just go on. What you find on the clean water side, you don't normally need filtration, maybe a manual filtration. But when we get into sort of what I call the wastewater side, sample presentation is key here. And that's to allow for longer levels of maintenance. What we find in the UK, certainly within the water companies, they're doing a lot of demanning sites. Everything's being run like a factory farm. Managers, process people are into remote diagnostics. So therefore, they will only go out on a failure. So the challenge they're providing companies like ABB is how can you make things robust? How do you make things reliable? But also, how can you make things that servicing intervals are a lot longer? Julian and I were at one water company where the aim of one water company was to actually sort of put a stick in and don't do any maintenance at all. So these are the sort of challenges that we have now and the future. If we look at these two, the reason why we've used these sort of products for a number of years is, one, you can see that it removes suspended solids down to 60 microns. Great. Two, it's actually self-cleaning. So it takes so like a centrifugal force, takes water in, and then actually sort of pumps it out and cleans. So therefore, you can see that you're not having to actually lift things up or to replace things. And also the micron pore size allows us to play, the mesh size allows us to play depending on the application. So let's have a look at some of the sort of case studies that we do have here. The first one is probably the easiest of all, really. You can see here it's normally potable water. We've got here sort of treated water, and that could be chloramination. It could even be raw water. It could even be final water. But it's that part of the clean water cycle. And on the right hand side, you can see an array of Aztec monitors. And typically, all you do there is a monitor to a wall. You're bringing your sample onto a side pot. The instrument itself can tolerate solids up to 100 micron, and with a flow rate between 200 and 500 mils a minute, you find that you don't really need filtration. And typically, the monitor will just run, and you would probably clean that side plot, once a month, once every 2 months. Pretty easy, standard, no need for filtration. You then get into sort of what I call the sort of river intake or raw water. Now, this is quite an interesting area for us. Typically, I've seen two types of installation, one being using a manual filter and the other is using an auto filter. But one thing we do, certainly with ammonia, to help any blockages or any areas, we tend to add an acid wash to this. And the reason why this is down to sort of the chemistry and also solids. And it's that sort of acid wash which allows then for the actual maintenance and service side intervals to be a lot easier. But the key thing here will be the solids levels. And the interesting thing that we've noticed is within the solids, depending on different water companies, different water sources, we talk about 100 microns as a sort of molecular size, but solids are different. They come in different shapes. Whether they're clumpy or whether they're sort of sedimentation or whether they're powdery, they're all different. And that's the thing that you cannot always sort of look at and understand. This is an example of an installation within Severn Trent Water, a typical installation. And what we've noticed with the water companies is there is not a one standard fits all. You've got here a monitor, running monitor, being used on sort of treated water, but you can see that we have an inline automated filtration system. And if you look on the picture on the right hand side, the benefit of this this is done by one of our contractors over here, but what both the water company and the contractor wanted is that they wanted a system where the operators did not have to go and do any maintenance. Now, myself and Julian think this is overkill because we have many water companies that will just use a simple manual filter. But you can see on the right hand side, the actual water quality is actually fairly clean. And also the sides, they're not being, there's no side buildup of solids. So you know that typically that water is actually quite clean. But obviously from our point of view, we help the customer with what they need to actually look after. We've done a lot of work with Yorkshire Water, and the reason that we are a framework supplier for Yorkshire Water for the Aztec monitors, ammonia being a big area. And they were challenged 2-3 years ago due to their sort of compliance and regulatory commitments to the drinking water, etc., where they had to measure a large number of final effluent points. This was because they were being fined for breach of consent. And certainly the environmental agency within the UK is very hot on measuring these points. So myself and Julian were sort of doing some site surveys, but you can sort of interesting thought about the installation of ammonia and a sampling system is you can see where are you going to put it. You've got walkways here, you've got small areas on aeration lanes, you've got a final discharge on the left-hand side where you're trying to find. So this is always an interesting point to get a sort of reasonable sample that you can actually take a measurement from. One of the first installations that we did in Yorkshire was actually fairly simple. It was done by a sort of a local contractor, and actually worked pretty well. The picture on the photo on the right hand shows you a simple kiosk with ammonia monitor. The left hand side shows you where the sampling point was behind, etc. Very benign conditions, not really stormy. And then obviously you can see the filter that we had. We did start off with sort of a nylon filter, thinking around about sort of the 50 microns. Experience taught us that we could go up to 100 microns, but also we went to a stainless steel system. This was a bit more robust and also could be cleaned quite quickly and easily. And that allowed us then to sort of allow the contractor and the water company to utilize the system. But one of the challenges that we have is, if you see the picture with the side pot in the middle, you can see how dirty that was. And the interesting thing about ammonia monitors, especially the ion selective, they are quite robust and can take quite a high degree of debris before needing some kind of maintenance. But one of the lessons we learned there is how can we actually in sort of improve the system to allow it to actually run further, greater than 3 months. One thing we've sort of observed with certainly working with contractors is sometimes the knowledge is not quite there in the UK. They get an application where they have to measure final ammonia, and you can see here on the left hand side a simple kiosk with ammonia monitor, filtration. On this one they were using a manual filter which was 100 micron, which is just, I think it's actually some rope, which was a bit strange, but you unscrew it, clean it, and put it back in. But if you look at the central picture, you can see actually that the final effluent, actually where you placed the filter or the submersible pump was very, very key. And the right-hand picture shows sometimes it's worth looking at that application, because you can see here, they were just using a filter. Not a sample pump they were using, not a filter. They were just using a sample pump. So they were just extracting the sample, and you can see, I would say they got it in the wrong place because it's quite a lot of solids on top, etc. But I would have put that sample pump somewhere else. But also I would have probably used a filtration system as the primary source rather than just relying upon the manual filter, because I think that was then putting work onto the instrument. And the issue we found there for the customer was that their maintenance levels were a lot higher. So it's about the understanding of that installation and where best sometimes to put the filtration or the sampling pump. So we've gained a lot of experience and sort of honed and refined our system. This was another system within sort of wastewater, within final effluent, within Severn Trent Water. And you can see here we were using sort of 100, and actually went up to a sort of 200 micron filter here on a rotor flush. So that allowed sort of cleaning, but also allows it to actually take in more sample. So therefore it could last longer. We had we called this our sort of primary filtration system. We then went, as you can see in the middle, third picture from the left, we didn't have a secondary filter, and we were sort of seeing some solid buildups. Now, typically for this site, which was sort of unmanned, they did ask us about, well, can we sort of improve the filtration type system? So we had a look and we said, well, let's see what we can do. So what we tended to do then is that we'd put a sort of what we call a secondary filter, a manual, an easy clean type system, so metal mesh. And you can get these up from about sort of 50 micron up to about 400 micron. And typically when we sort of put a primary and a secondary system, we tend to say maybe go up to say about 300 micron on the primary, and then we bring this down to about 100 micron. But you can see on here that this is installed. It's just unscrewing that, give it a quick wash and put it in. But this allowed two phases. One, we didn't have to touch the primary filter for at least 3 to 4 months. That stayed clean because it had a greater pore size and was able to actually produce sample. And then with this secondary filter, this allowed us, up to 2 months before doing anything, any cleaning, depending on the sample, and also depending on the type of year, because obviously final effluents can go up and down with solid levels depending on the time of year. But you can see on the right-hand side, we had a reasonable compliant side pot, which was very clean. And that was great because that meant the instrument just carried on working to the normal maintenance regimes. The other thing that we have done, and we've done a lot of work, is, as you saw earlier in the presentation regarding a debubbler type system. And this was quite inspiration from one of our service guys who had used this. He said, all we did was we modified the sample pot, and that allowed then for the sample to flow through. We did some modifications on the actual inlet side of it, and then we were able to actually sort of bubble any solids away. And that was just making sure that any excess solids were then taken out rather than being taken into the monitor itself. And you can see again, if you can see on the right-hand side, quite a good area of the solids being used. We'd obviously reduce that, but that certainly worked and helped the instrument work and perform to its optimum best. Another area, this is about sort of solids really. This is sort of my sort of final sort of set of slides here. We've done some work with sequential batch reactors on the wastewater side, and this really is sort of looking at sort of digestion of the sewage with bacteria. These are on a sort of like a metal disc, and apart from sort of getting up to the instrument itself, you can see a sort of section A, section B on here on the two reactors. For me, there was initially nothing seemed to be an issue. If you look at this, we were just sort of testing when we were doing some setups and trials with them. But you can see on the left-hand side, we seem to have very good clean water. You can see in the middle picture here, we had sort of like these little discs and yeah, nothing issues on the sample quite happily here. And you can see on the right-hand side where we were taking the actual sample to the instrument. However, we found that by initially we thought, well, we'll put a 50 micron in. It should be easy enough. There's not really much solids, but we had to do some changes. And reason why it's quite an interesting learning point actually here is that you can't quite see it on the two picture on the middle and the right hand side, but if you look deeply in, you can sort of see like sort of a powdery black substance. And what we found here is the solids, instead of being sort of homogeneous or clumpy in that way, it was like a powder. And what I meant by that, it was very, very fine, and it sort of clumped together. And what it did, it actually sort of covered the whole of the mesh. So even though we had a system that allowed us to actually backwash, the system would just clog up. So we were sort of scratching our heads with the contractor thinking, what do we do? But we overcame this by actually going up to a 300 micron filter. So when you look at sort of ammonia monitoring, look at reactions and sampling conditions, you really do have to get the filtration right. And sometimes it's trial and play. So it was quite an interesting application, which we actually resolved. So this is my last slide. We've been doing a lot of sort of wastewater ammonia applications, and the monitor is itself, it's a key thing. But why are water companies doing this? There is change. Let's talk about regulation, tighter consents. What we find is that DWA and the Environmental Agency, if there are any breaches, we see this all in the news, they will fine the water companies. They also, with their business plans, they find that they have to make these adjustments to make sure that they get their budgets pushed through. The other thing that we're seeing is really about how can they improve their wastewater plants, their cleaning plants. And this is we use the phrase factory farms. And it's about optimizing the process, which they've not done for many years, and ammonia is a big one. Energy, as we all know, is one area, and the process. So they're looking at savings, and they're making sure that first they comply, two, they can get savings, and then they get performance and process conditioning. The other thing that this is quite interesting is that this has led to other areas on the wastewater side where we're doing some work on phosphate and iron dosing, which to sort of look at sort of chemical dosing. And this lends itself to sort of certain savings that we're doing. So before I hand over to Julian, I'd just like to sort of summarize by certainly our experience on this is that the ammonia monitor, yep, it is robust. automatic calibrations. Using sampling techniques allows us to make sure that the customer and the operators have to do very minimal maintenance, and I think that certainly helped. Key selection of filtration, very, very important. The add-on of things like your acid cleaning or using debubbler certainly makes sure that the instrument works a lot better. And the thing that we've obviously used is to make sure, certainly with chemical costs or reagent costs, we have sort of built-in eco modes that allow us to actually improve and do longer optimizing runs. And the one thing that certainly helped our water companies is we've gained a lot of experience, and we always insist on going to sites to actually look at the application, because all you'll get is a green site with just a field with a hole, and they say, well, we just want to measure ammonia. And certainly that allows us to help and do some monitoring systems. So what I'm going to do now is thank you. I'll leave questions to the end, and I'll hand you over to Julian Edwards. Thank you for your time.
Thank you very much, Mike. Good afternoon, everybody. Thank you again for attending this presentation. So my side of the presentation is mixed liquor suspended solids, or I'll probably refer to it most of the way through as total suspended solids. So I'm going to kick straight off, if I may. An agenda, just running through some typical applications, a tiny bit on the actual instrument sensors that we use for this measurement. Some similar slides to Mike on installation and maintenance, and then a couple of case studies that we are running, actually currently running now, and just bringing them to a conclusion. So the timing is actually pretty good for this presentation, and obviously we'll do a Q&A at the end. So you saw this slide before from Mike. I've just chopped it down where we're looking at total suspended solids is predominantly in the wastewater side of the water industry. So from an industrial effluent discharge, either down the sewer or back into the environment, and then from any activated sludge processes down to final discharge, obviously for compliance monitoring when you're discharging back into the environment. A couple of just pictures of typical installations. So just to show you kiosks with sampling chambers. This is for obviously effluent discharge. We also look into ASP lanes, activated sludge process aeration for suspended solids, typically for optimization and control. And one that's very new to us, which forms part of one of my case studies, is RAS, recirculated activated sludge. And this is, I'll talk about this in more detail towards the end of the presentation, but it's a pretty interesting application for us to look at. And again, sorry, one slide same, this is final effluent discharge, and looking at total suspended solids, and this really is for compliance monitoring, reporting back to the Environment Agency. So pretty key measurement points from a process and a compliance point of view. So the system that ABB provide for measuring this is we have an AWT420 transmitter. This can be a single or dual input transmitter. I wouldn't say that for plugging one or two sensors into. And our total suspended solid sensor is called the ATS430. It has a range of 4,000 NTU, or a range of up to 100,000 milligrams per litre. It is a continuous measurement. I is sticking a sensor into a process and no reagents required at all. Very quickly on the transmitter, this is a relatively new transmitter to ABB, to our portfolio. It's all plug and play, where you can select what sensor modules, what sensors you want to plug into the transmitter. So it's just a quick show of how flexible this product is, but we're not here for that. Some of the other key features of the transmitter: we do PID control. We can do both channels, so we do dual PID control. Anything the sensor, any keystroke, anything's entered on the transmitter, or any errors of stuff, everything is logged, so you get a full audit trail of anything that's happened in the process. We also, from the digital side, we have a Bluetooth connectivity, so you obviously all password protected, very, very tight cybersecurity on this, but it allows you to upload if there's new software or something from your phone directly onto the transmitter. And also, Mike touched on QR codes. You can, if there's problems, you can scan the QR code, email that back to ABB tech support, and we should be able to hopefully help identify what the problem is that you're reporting. So a little bit, just a couple more slides on the instrument itself. This is about the sensor. We say it's primarily a turbidity instrument, so we are using the nephometric turbidity method. So we're measuring light scattered at 90 degrees. So yeah, a very industry standard measurement for this. The sensor itself, as you can see on the screen, it's a fully sealed sensor. You can have a choice of probe materials, stainless steel or titanium. We have an automatic wiper function, cleaning function, which is programmable, very much dependent on your application of how often, think of a windscreen wiper on your car, how often you set that to wipe. It says there the sensor itself is fully sealed, so unlike some of our competitors, the only real maintenance on this outside of things like verification calibrations is changing the wiper itself, and that's just a nylon nut that you undo and take off, put a new one on. So we've absolutely reduced the level of maintenance to these to the bare minimum. The optical is a sapphire glass, so it's very resistant to abrasion and bleaching and things like that. So it's perfect for the job. And the actual body itself, it's resistant to high temperatures. We can go up to 60 degrees and 10 bar pressure. And probably more importantly, from we say proven performance, we've did this with did our test. We have M certification for this product, for the sensor itself, and for the transmitter that it connects into. One of the key features of this sensor, I won't spend too long on this, is we've got something called adaptive software, and it's with the total spent solids measurements, it can be quite a choppy measurement, quite spiky, just by nature of what we're measuring. And by using this feature, we're able to sort of smooth out the readings. The two graphs, Fig 1 and Fig 2, I'm charging through this just because time isn't really our friend, but it's where our customers are using this feature, it's just getting a better traceability, without all the noise in it. So people are thoroughly finding this feature of use. And to support the ongoing maintenance of the sensor, we provide calibration kits. These are using I think the Perspex puck, Perspex calibration pucks. We do a high and a low puck, and we do it for 2 ranges. So you can basically try and cover the measurement ranges within the application. So you select which pair of pucks you would use, depending whether it was a final effluent or ASP lanes. So we've put together a really nice little system that allows you to perform verifications and calibrations using dry standards. You can also introduce, do a primary calibration using a wet formazine standard as well through the system. So I think we've really covered it well from a maintenance and support point of view. And the last one on just a bit of the tech specs, as Mike has shown, there are many, we're talking typically about 3 or 4 applications in wastewater, but they're all very different from a point of view of how you're trying to get a measurement from that application. So we have multiple methods of being able to get this sensor into your process. So, and there's a series of pictures at the bottom of the slide showing you what we can do, from a chain mount, dip hole mount, handrail mount, flow-through cell, or even a hot tap retractable system going directly into a live main, and it's designed to be removed live from the process as well. So many options when you're looking at your processes and applications. So you've seen this slide before, but I'll use it again because it's absolutely key to what we're talking about. So we come across many types of applications, V-notch chambers, ASP lanes, RAS. So you can see all these, and they all come with their own challenges of how we get the sensor into the process. I mean, I do go on about a lot. This is from me, to get yourself a reliable, accurate, repeatable measurement. It's key of where you place the sensor in the process. And when you're doing that, that's also from a point of view of maintenance. I say it's an old adage. It's something I say all the time. If it's not easy to get to and maintain, it's probably not going to get the love and attention that it needs. So at the point of when you're surveying sites, looking to put these sensors in, some thought should be put into that of just making sure, one, it's representative of where you want to be measuring, but two, people can get to it relatively easily. So the general maintenance, there's a couple of pictures on the side, but that's there. I'll talk about those as part of my case, one of the case studies. But as I said, with this sensor, it's pretty straightforward from a maintenance point of view. It says sensor body and optics. It really is checking, occasionally lifting it out for signs of fouling. If there is fouling around sensor, it's nothing more than wiping it down. And the only what I'd call potentially technical maintenance is periodically changing the wiper blade. And these wiper blades, you can get 8,736 wipes on a wiper blade. And once we get to that time, you get to that number, the transmitter will actually let you know, saying it's time to change the wiper blade, but it will keep on working. So it's very simple in that point of view. So from physically taking out, cleaning it, then we talked about verification, either using our calibration kits that we can provide, or doing, which is more common than ever now, is probably doing what we call in-process calibrations, which I'll come on to when we talk about one of my case studies. So, right, I'm straight into case study number one. There's just two. Now, this first one is for recirculated or recycled activated sludge, or lovely known as RAS. Where we're doing this, they've got 4 bell mouths where they are obviously where the RAS is being recycled from. One's bell mouth for each of their clarifiers. At the moment, or how they've been doing it for years and years, they're typically looking for a RAS concentration of about 4,000 milligrams per litre, plus or minus 1,000 either side for what they return back. And what they have to do every day, the right-hand picture will show you, they have to go down, take a sample. You can see this little beaker on a rope, take a sample back to the lab, filter it, dry it, weigh it, and get a result. And then if they feel the RAS is either too high, concentration of suspended solids is too high, too low, they have to manually, in the left-hand picture, you've got some pen stocks. You have to manually control those to basically either increase or decrease the amount of RAS you're returning. And that's something they do pretty much on a daily basis. So what the goal here was or the aim here was to find a sensor, a reliable sensor that you could put, as you can see in the right-hand picture, put directly into the process, and would it mirror their lab results? Would it be reliable? Would it be accurate and consistent? And if that is the case, then the next big step, which is the huge step, is then looking to automate the control of the pen stocks themselves. So using 4,000 would be your set point, and there'd be physically controlling or remotely controlling the pen stocks to keep the RAS within very tight limits. And I don't know how clearly the graph comes out, but the ABB probe is the blue line, and you can see it mirrors really pretty tightly to their process throughout. This trial's this is from March last year to June, and obviously I'm actually down on site next week finishing off the trial. But since about August, we made a couple of changes, and it's tracking really well. And what's great for us, the feedback from the process team is really good. So hopefully we're going to do some good stuff here. And far through the slide, this is just showing about methods of performing in situ calibrations using our kit, and then comparing it to a laboratory method. The last one is final effluent monitoring, and I see I'm running out of time here. We've got, this is it's final effluent chamber. The challenges here, the measurement itself should be really easy for us for this probe, because it's the MSA approved product, which is for final effluent monitoring. So we were very confident that the measurement would be easy, but it's all about the application. Now it's not easy to see here. This chamber can be quite flat. It's a base load system, so depending on what's the weather and what's being flushed down the toilets, the velocity of this flow can change very quickly, and the depths can change. But typically it's quite a low level flow, and with our the sensor, we have to have it at least 30 centimeters below the level of the water, because otherwise light will get to the optics and can cause problems. And also it has to be 30 centimeters below the level, but it's also going to be 5 centimeters minimum away from any surfaces, i.e. the sides or the bottom. And when we had to basically stick this on the bottom, but to give us this 30 centimeters, but being right on the bottom, it meant there was weed all down there, which was then moving around and going across the optics and causing all sorts of problems. So eventually we had to lift it slightly just above the bottom, but we weren't quite 30 centimeters below, and we were getting light. So what we did, it's hard to see, we just made a little guard, I call it a sunshade, that we fitted to the top of the sensor. It's basically like a half piece of guttering. And that was highly effective in stopping light. So we got rid of all those problems. But then the next thing we encountered was when we moved into the spring and summer months, was what you can see here. It looks like weed, but it's actually insect larvae. It was disgusting. And this was building up during particularly the peak summer. Within 2 or 3 days, this was just getting coated in insect larvae. And what you can just about see here is the wiper itself, the optics, if my cursor's coming over, okay, there, were being kept pretty clean. But the problem was every time we wiped, within 10 minutes, this larvae, it just was wriggling across the optics again and causing all sorts of problems. So we don't know how to get around this. It's nothing to do with the technology we're using. It's a freak of this site and where it is. But except for that incident, here's just some data from just over a month's period. It looks quite choppy, but on the y-axis, you can see that's from a range of 0 to 25 milligrams per litre. So it tracked actually pretty well within these bands. And I say, given the overall range of the instrument, it's 0 to 4,000, and we're down to about 5 to around 15 on average NTU milligrams per litre. So again, outside of the insect larvae, a very successful trial, and we were delighted with the outcome, as was the customer. And I think that takes me to questions.